Voila.
Okay, do you want me to keep sharing my screen or?
That's fine. Yeah, I'll have my video on. Are we ready to start, Susie, or you want to wait for another minute or two? Or?
Let's get started.
Okay, all right, great. Good afternoon, everybody. My name is Vallabh Das. I'm professor at the College of Optometry and president of the UH Faculty Senate. And so it's my distinct pleasure and honor to welcome you all to this first seminar in this Assistant Professor Excellence Speaker Series. Since this is the first of the year, let me just give a brief summary of the APeX. So it's something that the Faculty Senate and I personally I'm very proud and excited about, right? So the goal of the APeX has always been to showcase the groundbreaking research, scholarship, and creative activity being undertaken by UH early career faculty. Often much of the attention is given to senior faculty and well-established research groups. And young faculty, after the excitement of being hired, are left to work away in their labs and offices as they are striving to establish their career and work towards tenure and towards, as they're progressing in the career. And so what the APeX series tries to do is to break the cycle and give the young faculty member the opportunity to tell us about their work and tell us what excites them in their domain of research, scholarship, and creative activity. So I'm always excited to hear about all the groundbreaking new stuff that is going on here at UH. It also provides a young faculty member another opportunity to establish networks that potentially help them in their career. And so if that happens, that's a bonus, of course. I want to thank Dr. Susie Gronseth as the committee chair and also other members of the Community and Government Relations Committee of the Faculty Senate for managing the process of putting together the APeX program. It's a lot of work, I know. I also know that getting selected for the APeX is very competitive as the committee receives many, many applications and there are only a few slots. So it also takes a lot of effort on the part of the selection committee to review all of those excellent proposals and to come up with these final selections. So their work is also much appreciated. It also means that the speakers you'll get to hear from over the course of this year have some truly exciting work to showcase. So let me just go on then to the introduction of today's speaker. I'm excited to introduce Dr. Emily Beverly from the Department of Earth and Atmospheric Sciences of the College of Natural Science and Mathematics. Dr. Beverly got a bachelor's degree in geosciences from Trinity University and a master's degree from the Department of Earth and Planetary Sciences at Rutgers. She went on to get a doctorate also in geology from Baylor, following which she did a couple of postdoctoral fellowships, one at Georgia State and the other at the University of Michigan. Since 2018, she's been here at UH as an assistant professor in the Department of Earth and Atmospheric Sciences. And she leads the Human Environment Interactions Research Group. Dr. Beverly maintains current funding from the NSF, many more proposals under review and preparation, has a solid publication record. And actually, one of the fun things that I saw on her CV was that she gets to travel to many interesting areas of the world, like Kenya, Tanzania, and Armenia for field work. It actually makes me a little jealous when I think about my own work, which seems so much less cooler in comparison. So without further ado, I'll turn it over to Emily to tell us about using soils of the past to reconstruct the landscapes of human evolution. And Emily, if there's any part of your bio that I did not talk about or you want to tell us about, please feel free to do so before you, start up on your talk.
No, that was great. Thank you. Just let me get my PowerPoint going. I'm gonna do the little laser pointer. There we go. Okay. So, yes, I get to travel a lot of very cool places. And so today I'm going to talk to you a little bit about my work trying to understand what's driven human evolution and talk to you about some work that I'm doing and that I've done in Tanzania and Kenya. So a little bit of background, because this is probably not something that y'all think about every day, but what I'm interested in is trying to figure out what drove our evolutionary history. So this is just showing through time all the different species of hominins as they appeared and disappeared through time. These ones in red are the ones that are most similar to us. And then here we are, this last little bit of chunk of time about the last 300,000 years. And so I'm interested in trying to figure out what drove all these splits and extinction events, as well as changes in behavior. So changes in bipedalism, changes in our diet, how we develop different types of stone tools, as well as changes in our brain size and things like that. And so one of the drivers that's been, this idea has been around for a really long time, is that one of the drivers of changes in human evolution. So this is showing you some of those branches. This isn't all of them that was in the last figure, because this only goes back 4 million years, but it's showing you some of the branches. And what people have noticed is that through time, some of the major changes, so there's branching events here, extinction events here, some more extinctions at this time period. And these all occur during really important changes in our Earth's climate. So here we have the intensification of northern hemispheric glaciation, which had a big effect on our climate. Walker circulation develops between 1 and 2 million years ago. This had a big impact on our climate because it developed this circulation that goes east and west across the Earth's surface, changed a lot of our climate patterns. And then about 1 million years ago, we switched from having cycles of glaciation that occurred about every 41,000 years to about every 100,000 years. And so, what we started to notice is that there's probably, this is related to climate in some way. But part of the problem is that we don't have enough climate records to really understand if this is truly what's driving it. And so what I do is try to understand how I look at climates on, I'm looking at stuff on land, and I'm trying to understand how did these changes in climates and environments affect the evolution of humans. And so this is just to kind of demonstrate what I mean. So this is one of the Acheulean stone tools. So it's about 1.6 million years old, very, very large, and over between 1.6 million years and about 70,000 years, we figured out how to make these very small, this is a middle Stone Age Lavawa point that, it takes a lot more skill to make these very, very small stone points. And so, I'm interested in how we got from here to there. So this is a site in Tanzania. This is Olduvai Gorge. And this is from a site in Kenya near Lake Victoria. And so, how did we get from here to there is really the question I'm trying to answer. And so in trying to answer that, one of the things that we come up against working in Eastern Africa to try to understand this is that Africa is really big. So most maps that are kind of shown globally of the world don't accurately depict the true size of Africa. But if you, to kind of give you a scale of just how big Africa is, this is showing you all of Europe, the US, China, India, all fit within the continent of Africa. So it's a really huge area that we're trying to understand what's going on. And so, we have to have a lot of different records across this huge area of space to really be able to figure out what's going on across this huge area of space, but also what's happening through time to understand why we were evolving and creating new technologies. And so that's one of the complicating factors, is just that Africa is such a large place. What mainly I've been working on is in areas in Eastern Africa here. And we know that humans started migrating throughout Africa and out of Africa. So, and anatomically modern humans, just like us, that started migrating out of Africa and into Eurasia around 60 to 70,000 years ago. But this has become more and more complicated because now we're getting more and more evidence that, you know, we migrated out of Africa multiple times, but not all of those migrations were successful. And so, you know, this history of trying to figure out what drove us out of Africa has really become a big issue, because it's every time we find more and more sites, it becomes more and more complex. So this is just showing you that, you know, it started around 60,000 years ago, and then by 10,000 years ago, we were all the way into the Americas. And so what I've been doing is working here in Eastern Africa. So this is Ethiopia here, Kenya here, and Tanzania is down here. So this is kind of looking north up across the continent of Africa. So I've worked at a variety of sites across Eastern Africa. I've worked on outcrops like this. So we're looking at rocks that we can kind of see at the Earth's surface, but I've also worked on cores that have been collected in near very famous archaeological sites, trying to get a longer term history. And the other thing I've done is also work on modern soils to try to get us some additional data that we can use to better interpret the past. So I'm going to focus in on these three kind of areas today. One is here near Lake Turkana, another site called Olorgesailie in southern Kenya, and then the modern work that I'm going to talk about at the end is in Tanzania in the Serengeti National Park. So that's just a little bit of background on where I'm work. So wanted to talk a little bit about how we actually measure climate in the past. So to understand how climate changes in the past, we use what are called climate proxies. And so these are signals that are preserved in the past that we can then relate to climate. So say, you know, changes in pollen could be related to changes in precipitation or changes in temperature. And so there's all different types of proxies. I've just kind of put some common examples here. So you've got pollen here. In ice cores, people study the gases that are in bubbles in the ice cores. People study tree rings, looking at the thickness of the tree rings to understand climate. And people also use things like waxes that come from plant leaves, so that they're causing the leaf to look so waxy. Those waxes we can also use to understand relate to climate. So those are all different examples of climate proxies. And I specifically work on proxies that we find in soils. So I use signals that are preserved in soils of the past, and the word for that, the name that we use for that, they're paleosols. So these are just, you know, past soils. And so these are some examples of some different paleosols that come from one of these drill core sites. So we can look at the chemistry and the different features that we see in these paleosols to better understand things about the climate and the environment. So one of the sites that I'm going to focus a lot on is talking about the site called Olorgesailie. So this is from a picture from when we actually collected the core. So this is the drill rig that's collecting the core. So this is just like a drill rig that would drill for oil or water, except that they use a slightly different drill bit. So this is a diamond drill bit on the outside, and then it has kind of an open hole in the center. And so what we can do is basically cut down and pull up slices of rock from beneath the surface to get really long-term records. So we can do this. So I look at things that are in cores like this, but I also look at a lot of outcrops about this with paleosols in them. And so much of what we, just like all of geology, much of what we know about the past, we learn from kind of what's happening in the modern, and we apply that to the past. And so what we know about modern soils, but what we know about paleosols comes from our knowledge of modern soils like these. And so we can study modern soil features like the ones you see in here, and we can also study chemistry of these different modern soils, and then we can apply it to the past as a proxy to better understand what the climate and the environment was like. So what would affect chemistry in a soil? So these are 3 different examples of very different looking soils. So they have very different textures here. You can see there's different minerals in here. There's a lot more organic matter in this one. And the colors are very, very different. And so these are from very different places in the world. And so depending on, there's 5 different features that affect soils across a landscape. And so those different features are climate, organisms. So climate would be things like temperature and precipitation. Organisms would be anything that would burrow through the soil, termites, all different fungi, other bacteria, that are anything living in the soil. They all have a big effect on the soil. The relief or the topography of the landscape, so whether you're at the top of a hill, kind of on the side of the hill, or at the bottom of the hill, affects how the soil would look and its properties, as well as the parent material. And so parent material just means where the soil is coming from. So what type of rocks make up that soil. And then finally, the last thing is time. So time, depending on how long that soil is forming on the landscape, will affect the soil chemistry. But the most important one of these functions of climate is that functions is climate. And so it has the biggest impact. And so let's go back to these soils that we were looking at originally. So this is going from a really arid environment to a really humid environment. And so you can see that, as you go from dry to wet, that it really changes the types of soils that we get on the landscape. So, when it's really arid, we have very little organic material. When it's temperate, we have more organic material. And when, if it gets humid enough, so this is probably something that has 4 meters of rain per year, basically everything starts to get leached out. So all those different elements can get leached out with the more water that we have flowing through the soil. And so we can use that chemistry and relate it back to climate. So basically, the more water you have, the greater amounts of different elements will be removed, like aluminum or sodium or calcium. And the less water, the less that is removed. So basically, we can use this, measure this chemistry, because this chemistry is something that we can measure in the past. So we can take a bulk sample of the paleosol and we can measure that chemistry in the past. And so therefore, we have a nice proxy for climate. So this is an example of one of those proxies. There are a number of different ones. This one's called the chemical index of alteration minus potassium. And so it's relating a ratio of aluminum, calcium, and sodium. And we can relate that, those ratios of those elements to mean annual precipitation here. So you can see we have a nice linear regression line through this. So that's the equation here. So then we can measure these oxides in the past, calculate this chemical intensive alteration, and then we can use this equation to calculate what the precipitation would have been in the past. And so we have different proxies like these for things like pH and multiple ones for precipitation, ones for temperature, all just using what we know about modern soil chemistry and relating it to the past. So this is an example of one of those paleosols in one of the outcrops that I worked on near Lake Victoria. And so basically we would collect a sample here, bring it back to the lab, measure the different elemental oxides, and then calculate the mean annual precipitation. And so then to figure out how things are changing through time, we would just collect samples from multiple paleosols. So in this outcrop, we've got a paleosol down here, a paleosol here, and then a little higher, there's even another one. And so we can see how things are changing through time. And we found a lot of different fossils in this site and some archaeology, so some different Middle Stone Age points. And so we can relate those changes in climate to changes in the stone tool technologies. If we want to look at things over longer timescales, so this is, we're kind of limited with an outcrop to how much is exposed at the Earth's surface. If we want to look at things in longer time periods, what we can do is collect cores. So there have been a number of very large projects that have been started. They started in 2013, I think, to collect cores from close to very famous archaeological sites to try to get better long-term records. And so what I'm going to talk to you about is one of those called Alorgesailie. It's called the Alorgesailie Drilling Project. And so Alorgesailie, again, is here in southern Kenya, and it's a famous archaeological site. It's got tons of mammal fossils, as well as different stone tools, and even some things like pigments that they find. So it's a very famous archaeological site, and so that was why it was selected as one of these sites to get a core. And so what they did is this is about 50 kilometers from the archaeological sites. The archaeological site's basically on the other side of this volcano here. And so we collected these cores, and the hope was that we'd get these really nice laminated cores like this, where we have, this is a lake deposit, and it's made up of these tiny organisms that make their shells out of silica. And so those organisms live in the lake, and then when they die, their bodies fall to the bottom of the lake, and over thousands to hundreds of thousands to millions of years, they slowly build up and make these nice layers in the lake. And so the useful thing about these diatoms is that we can tell things like whether the lake was shallow or deep. We can tell if the lake was freshwater or saline, so we could, not something that you could drink. And so we can use these diatoms as a proxy for what the lake looks like. And so what they hoped is they'd get this really nice long-term record of the lake history that would tell them something about, the long-term history of this, the climate history of this region. And what they ended up finding out is that the lake dried up a lot. And so this is a paleosol right here. So this would have represented a period of time when the lake was completely dried up and it was land. And then on top of it here, we see there's another lake forming. And so through time, what was happening is that it was basically shifting really rapidly back and forth between land and lake, land, lake, land, lake. And so this is an extremely rapid transition. This is not normal for the lake to be so with such a sharp surface here. Normally there's kind of more of a transition between the two. So this was very unexpected that we would find all of this evidence that the lake had dried up. And so that's me there. This is working. All the cores are stored at the University of Minnesota. And so I started working on this project to try to understand what was happening during kind of the land phases of this core. And so the whole reason this core was even drilled is this is the stratigraphy. So this is what the rocks types are from the outcrops that they've been studying for a really long time. And so all these red stars here are all the different archaeological sites that they've discovered. So these are evidence of stone tools or pigments. The younger stuff has pigments in it. And the problem with the outcrop, and the reason they wanted to drill this site, is because there's a big gap here. So there was a big erosional event here where there's about 200,000 years of history that is missing from this location. But there's a very distinct transition between using a Schulian, those big stone tools, to being able to create those smaller stone tools, the middle Stone Age tools, that happens between these two areas. And so we really needed to know what was going on here to better understand what was happening during this time period. So what drove the humans and hominins here to actually evolve and start creating this new stone tool technology. So was it actually climate? And so these cores were collected to kind of fill in all of these gaps in where we had erosion in the outcrop. And so this is part of a very large, so there's hundreds of different geologists and paleontologists and geochemists all working on this huge project. And so we had a lot of different types of proxies. And so quickly, I'll just go through some of the examples of the different types of proxies we were using. So this is using the diatoms. We could tell whether the lake was shallow or deep. We could tell whether the lake was fresh or saline. And then we also had a bunch of different proxies for the type of vegetation that was growing on the landscape. So we could tell whether it was more grassy vegetation or more woody vegetation. We could tell whether they were C3 plants, so they were more like trees versus grasses. And then there's even proxies where we can tell things like whether the grasses were short or tall. And so we kind of put all this information together in this much easier to read graph that kind of summarizes what's going on. So in terms of the whole reason that they were interested, again, is that there's a change in the type of stone tools that they're making. So they went from making these really large hand axes, a Schulian hand axes, to much smaller middle Stone Age tools. But there was also a big change in the organisms that were living there. So prior to about 500,000 years ago, there was a lot of very large, so things larger than an elephant living there. And they were also a lot of different species that are what are called hypergrazing. So they're arid adapted species. And after this time period, we have much smaller organisms. So a lot of the really large organisms died out and their diets diversified. And so what we were trying to do with this core was to try to figure out what's going on. Why do we have this at the same time we have this stone tool replacement? We also have this turnover in the different species. what drove this? And so what we were able to figure out by combining all these different proxies, including the paleosols, is that prior to about 400,000 years ago, we had really large, predominantly fresh lakes. And after about 400,000 years ago, we had much shallower lakes. They were more likely to be saline, and they dried up much more frequently. So we found a lot more paleosols in this interval. And so in addition to that, there were changes in vegetation. So it went from being more of a grassy woodland to being more variable. We had shifted from short grasses to kind of tall grasses. And all of that, data ends up telling us that the resources that were available to the hominins and other organisms living there were relatively predictable prior to about 475 million years ago, or not million years ago, 1,000 years ago. And then after that, things became much more variable, and there was rapidly shifting changes of availability of these resources like fresh water that people require. And so, we were able to show that this change from predictable resources to things being less predictable ended up driving changes in our evolution. So we to adapt to these rapidly shifting levels of availability of resources, we ended up developing new stone tool technologies. So that's one of the projects I've been working on for a long time to try to understand what's happening with changes in the stone tool technologies. But the other aspect that I also work on that I wanted to talk about, it's kind of the more recent work that I've been doing, is using a specific mineral in these soils called calcium carbonate. So it's calcium carbonate here. All of these little white patches that you see on this core, so there's little white patches in here, those are all this mineral calcium carbonate. And so for a long time throughout Eastern Africa, we have used calcium carbonate to understand things about vegetation. So we know that over the last 5 to 10 million years, basically things have been shifting from a more woodland environment to a more grassland environment. And so what I've been working on is trying to improve some of our proxies that we have using this mineral calcium carbonate. And so this is where kind of my work on modern soils comes into play. So this is an example of a modern soil from Tanzania. And so this is in the Serengeti. And so I went out to collect modern soils, and especially to collect this little carbonate nodule here. So I was interested in trying to collect samples of modern soils to study the stable isotopes in the carbon and oxygen that's found in these calcium carbonates. So we can measure, we can react the calcium carbonate with acid and get CO2 out of this mineral, and then we can measure the different isotopes of carbon and oxygen using those using that CO2 that we've reacted with acid and the calcium carbonate. So this work uses what's called delta notation. And so here it's just the ratio of the heavier isotope of carbon to the ratio of the lighter isotope of carbon. And then the delta notation is a ratio of the sample that we're interested over a standard. And then we multiply it times 1,000 so that it's reported in parts per mil. So that's this symbol here. And so these these stable isotope proxies we can use to understand a lot of things about the climate and the environment. But as I'm going to show you, that we still had a lot of questions and there was room to kind of improve things. So this is just kind of a summary paper of a bunch of different records that are all trying to show you the same thing about, you know, what's happening globally during the evolution of humans, what's happening in like overall in Africa, and then here's what's happening in Eastern Africa, where I primarily work, where we have this big shift of in the carbon isotopes from more negative to more positive. And so we know what causes this in modern soils and paleosols. This all has to do with whether or not the plant is a C3 plant or a C4 plant. And so the C3 plants, like trees, have more negative carbon isotopic values, and the C4 plants have more positive carbon isotopic values. So, you know, we can basically get a picture of what the landscape kind of looked like. So, you know, if you have more positive isotopic values, it might look like something like this grassland here from the Serengeti. Something more like this is from closer to Lake Victoria, where you have more of a woodland. And here's an example of what a modern tropical forest looks like in Eastern Africa. So we can use these isotopes to as a proxy for what the vegetation was like by looking at the carbon isotopes. And so these isotopes come into play because of how different types of plants versus C3 versus C4 plants actually photosynthesize. And so the C3 plant part comes from they create a chain of 3 carbons, and the C4 plant is because they create a chain of 4 carbons. And so this C4 plant, C4 plants have this extra process where they try to, during photorespiration, plants are trying to, you know, bind the CO2, but sometimes they accidentally will bind O2 rather than CO2. And so this creates a lot of extra wasted effort for them. And so C4 plants actually evolved a way to reduce this problem. And so they basically can keep their stomata, the openings on the leaf surfaces closed more often. And so that makes them better adapted to things like arid environments, because they can keep more water in, higher temperatures, and also times when we have lower CO2 in on our planet. And so the difference when they, you know, as these plants are photosynthesizing, this C3 plant pathway ends up producing more plant matter that utilizes this carbon-13 isotope. And so that's how we actually are able to reconstruct this in the past, is because these C3 plants preferentially have more carbon-13, making their values more negative. And so we can then reconstruct what the plants were like through time. So this is what's happening in Eastern Africa over the last 10 million years. Basically, we're going from a more C3 dominated plants where we have lots of trees to more C4 plants where we have much more grasslands. But there's a big part of this puzzle that's missing, is that so when we measure these isotopes, we get both the carbon and oxygen at the same time. And so here's a plot of oxygen from that same time period over the last 10 million years. And there's no real trend here. It doesn't have a nice trend where it goes, you know, decreases through time or increases through time. But this oxygen isotope can tell us a lot about changes in precipitation. It could tell us about changes in the water source. So maybe we have more water coming from rainfall coming from off the Indian Ocean versus the Atlantic Ocean. But because there's a lot more variables that go into figuring out what these oxygen isotopes mean, people have kind of ignored it because they don't really know what to make of it, even though like these red lines here are from this site called near Lake Turkana that I talked about in the beginning, that there's clearly a kind of shift here, but we don't know what's causing that shift. And so I'll go into why that is a little bit next. So like I said, we know what's causing, in these soil carbonates, we know what's causing the carbon isotopes. It's the amount of C3 versus C4 plants. So, we've figured that out. We've known that for a long period of time. But we don't know what's causing the oxygen isotopes, and that's because we have different isotopes depends on where the water's coming from. So what the oxygen isotope composition of the water is. When it falls as precipitation, it then mixes with whatever water is already in the soil. It can also evaporate, which will change the oxygen isotopic composition. And so, it's a function, the water that's in the soil is a function of what the composition of the water is falling on the landscape, as well as, evaporation that's going on in the landscape. The other thing that complicates this is that not only is it a function of evaporation and the composition of the water falling on the landscape, but it's also affected by temperature. And so, these things are, it's very hard for us to know what temperature is and evaporation is in the past. And so what we needed was new proxies to be able to measure this evaporation and temperature in the past. And so over the past 10 years, we've developed some really exciting new climate proxies. And so the ones I'm going to talk about are clumped isotopes and triple oxygen isotopes. This is the kind of really cutting edge stuff that I've been working on for the past 4 years or so, to try to create new proxies to be able to interpret this delta 18O record that we have. That's very powerful, but we just don't know how to interpret it. And so what I did in 2018 was actually go out to the Serengeti and collected modern soil samples across this transect. And so this kind of goes from the most arid part of the Serengeti to the wetter part of the Serengeti here closer to Lake Victoria. And so, these are just examples of what it kind of looks like. So both kind of grasslands, it's just clearly drier here than it is here. And so these are some examples of the different soils that I was looking at. So this is one of the soils from the drier part of the Serengeti, and this is one of the soils from the wetter part of the Serengeti. So you can see that there's clearly some major differences, but both of them had this mineral carbonate that I was interested in measuring the isotopes. So the carbonates here kind of at the bottom, and the carbonates here in this one, in this soil profile. And so these are just examples of, different samples that I collected. So there's, a very large carbonate mass here. This has little bitty baby nodules. This is just as kind of a coating on this piece of volcanic rock here that accumulated on this soil. And so what I did was collect this sample, and then we measured the different isotopes on this carbonate to try to figure out how to relate these properties to a climate proxy in the modern, so that then eventually we can do it in the past. And so these clumped isotopes, this is very complicated, so I'm just going to kind of give the brief overview of what we're trying to do. So clumped isotopes we're using different what are called isotopologues of CO2. So we're looking for things that have, the same chemical formula, same bonding arrangement, but they have different isotopes. So these are examples of these different isotopologues. And so they have different masses for that reason. And so we can measure them in an isotope ratio mass spectrometer. And what we found out about 10 to 15 years ago is that the way that these isotopes clump together in CO2 is temperature dependent. And so if we can measure how much of these clumps we have in the CO2, we can figure out what the temperature was in the past. And so this is a plot showing you examples where they've done lab grown calcium carbonate. So this is the clumped isotope proxy here on the y-axis, and this is temperature going from 0 to 300 degrees C. And so we have a nice linear regression again here, and so we can use that to then, in the past, we measure this value, and we can use this linear regression equation to calculate what the temperature would have been. And so what I was doing is working on proving that this works in the modern. So this is part of a large body of work. There's a lot of people working on this, but I was kind of working on some of the soils that had high temperatures and in the tropics. Nobody had ever really done much with work in the tropics. So I was just showing, this is what the temperature should be. And this is what, the clumped isotope temperature shows us. So we were, pretty in line with what we expected. So we knew that this proxy for temperature would work in the tropics. And so then the kind of last piece of the puzzle is trying to figure out evaporation. And so that's where we can use additional isotopes of oxygen to try to understand this. So normally when we're measuring oxygen isotopes, what we're doing is measuring oxygen 18 in a ratio of oxygen 16. And only very recently have we been able to measure oxygen 17. It's really rare. It's very hard to measure because it is so rare. And so only in the past 10 years, really 5 years, honestly, have we improved our instruments to the point that we have the precision and accuracy to really be able to measure this isotope of oxygen. It's very easy for us to measure oxygen 18 and 16, but it's been very difficult for oxygen 17. And really the only ways it had been used, we knew about it. It had been used before, but it was primarily in areas of geology where you're trying to understand whether or not a rock came from another planet, because the isotopes were so far apart that it didn't matter if you weren't very accurate or precise, because it was far enough apart that it didn't matter. But only in the past 5 years have we really been able to measure this in carbonates to the point that we can answer questions about climate. So just kind of a brief overview of what we're looking for. So this is what we were predicting with this study, is that you have an oxygen isotope composition. So you have a range of precipitations here. And if it shows signs of evaporation, what will happen is that the oxygen isotopes will increase, and the oxygen 18 will increase, and it will decrease for oxygen 17. So this is what we were expecting would happen, but before this study, we didn't know. We didn't have, we had like 1 or 2 soil carbonate samples, and so we had to kind of test this on a modern soil to really be able to understand what was going on. And so this is kind of the results of that work. I know it doesn't look like very many data points, but this took me almost 6 months to do. It's a really long, complicated process, most of which has to be done by hand, where you're physically moving dewars from a trap to one trap and then heating them up to release the oxygen. It's a very, very long process. And so it doesn't look like very many data points, but this is actually a very robust data set for this type of study. And so again, here we have oxygen isotopes on the x-axis and 17O on the y-axis. And what this study showed from the Serengeti is that all of the cooler colors are from the wetter parts of the Serengeti, and the warmer colors here are from the drier parts of the Serengeti. And so we see this evaporation trend. So we see that the oxygen isotopes increase, and the 17O isotopes decrease as we get to the more arid parts of the Serengeti. And so this was really exciting to see, because it shows that this can probably be used as a proxy for evaporation. And so another way we could plot this is, again, where this transect was showing you across from the driest part of the Serengeti to the wettest part of the Serengeti. And so if we plot against this aridity index, which is just a measure of evaporation in a way. So the lower numbers here are going to be more arid, and the higher numbers are going to be more humid. And so we can see there's a clear shift between the samples that were collected from dry subhumid environments to semi-arid environments. And so what we're working on now is trying to expand this to other types of environments, like arid and hyper-arid environments and really humid environments around the world, to kind of fill out this plot so that we can really create a nice proxy for evaporation. And so the hope is that we will be able to eventually interpret this record and really be able to add some more pieces to the puzzle of trying to understand, why we have all these changes in morphology and behavior through time, and why we ended up migrating multiple times out of Africa and throughout Africa, and understand why we really changed these types of stone tool technologies through time. So with that, I will I've got it funded. This work was funded by a number of different places. There's a whole bunch of people involved in these projects, and it summarizes a lot of data that people have done over the past 40 years. So that's all the data. But now I'd be happy to answer any questions that people might have.
All right, thank you so much, Dr. Beverly. That was a wonderful seminar. And now we have time for questions. You can either put questions in the chat if you prefer, or you can simply unmute yourself and ask your questions. So do we have any questions?
I was wondering what the thought is that the correlation, you think the correlation with the human development is more through migration or through nutrition? Or I guess the two are very well linked, right? But it's because the generation of different tools, it must involve some additional, probably, cognitive or ability. So which would that be affected by migration or more, do you think, or by maybe nutrition as these environments change?
Yeah, so that there's a lot of argument about that, whether it could be things like nutrition, and as we changed our ability, basically one of the theories is that we outcompeted other types of hominins, because we were the most adaptable. And so we were able to adapt and eat the most kinds of things. And But the migration part of things, a lot of people think it might be more related to water and water availability. So it's kind of both things, because there's a lot of research right now trying to figure out, how much water do people actually need? Where was it? Was it enough to sustain people? Is that one of the reasons that we might have actually moved, because kind of the climate kind of changes in phases across Africa because it's such a big continent, and it doesn't all get wet or dry at the same time. And so maybe they're just following it as it goes wet and then it comes back down. And there's many theories. We don't have the answers yet.
I had a question on validation of the proxies. So, for example, one of the examples you gave was the chemical index of alteration, and this was a proxy for precipitation, I believe. And so the question is if that relationship between the proxy and the thing that you actually want to know, right? Could that relationship, could that change over time? How do you know that that would be valid, millions of years ago versus today? And then how do you explore that?
So that's kind of one of the assumptions we have to make in geology, is that the present is the key to the past. So one of the things that we try to do and one of the things that I'm working on, is that a lot of these proxies were developed in mostly in North America, and I'm now trying to make sure that we add data from Eastern Africa to try to make sure that we're kind of answering that question. But that's basically kind of the best we can do, is that, we assume that the same kind of soil processes are happening in the past as they are today.
Okay, great. Thank you. Do we have additional questions?
Yeah, so I had a question, maybe naive here, but so your analysis is based on migration out of Eastern Africa and in that area. Is it necessary to validate that against some other part of Africa, or is that you basically expect it's going to be the same wherever you do your soil analysis, for example? Within the continent of Africa. I mean, because I think initially you said Africa being so big and varied, I wonder what complication or that brings about.
So the point about Africa being so big is really, the point is that we need more and more data.
Right.
So I showed you, go back. So that slide. So I'm just working on these few sites, and so really the problem is that just in between these two sites across, this is northern Kenya and southern Kenya, climate does not respond the same. Partially because the East African Rift really complicates climate. So you've got the Rift. This is the western branch and this is the eastern branch, and it really complicates climate. And so we need, the point about that was more to show that we need lots and lots of sites, and we need more and more studies. And we can't just only, kind of the historical way was to just focus on one site and get really good records from one site. But we more and more realize that we need to have sites all around the continent. Not, I'm focusing on Eastern Africa, but there are tons of people working in caves in South Africa. And there's a lot of stuff going on in the Sahara. And so I just showed you kind of what I'm working on, but they're working all over Africa trying to do this, trying to understand.
And the data from these different sites just from across Africa are generally consistent when you talk about other aspects, like even with proxies or tools and some of the different things that you're concluding based on your analysis.
Yeah, so basically what we've learned kind of over the last 20 years. So this figure here that I showed, this is pretty old. It's from 2004. So a lot of this is kind of out of date, but it just is the best figure that I can find to kind of illustrate this. And so basically we have, it was thought that, there's this transition from woodland to grassland. And now as we've added more and more data, so I have another plot. So, now we've added a lot more data in the past 20 years. And so we've determined that it's a lot more complicated than we thought. And so that's kind of where we're at now, is trying to fit all of this together. And so that was a big goal of these drilling projects, is to try to get really long-term records that we could then use to kind of piece all of this together.
Great, thank you.
I was wondering, this might be outside of your realm, but do you know of any studies possibly regarding ancient DNA being pulled from these soil cores that could possibly help?
So in terms of ancient DNA, soils are not really a good place to find it because the weathering processes are so strong. There are people that are doing ancient DNA back to about 30,000 years or so, or 50,000 years on lake cores in Africa, and they're doing it in different swamps in Africa. This is actually DNA from teeth on modern humans, so that's what this is showing. But there are people trying to do DNA on other environments, but soils are just usually in Africa very oxidized, and so that kind of breaks down any of the DNA. But in some of these really anoxic swamps and lake cores, they can actually kind of get at, they can tell things like when cows arrived on the landscape and things like that.
Cool, thank you.
Mm-hmm.
All right, well, it looks like we're pretty much at time. So thank you again, Dr. Beverly, for your seminar. And yes, a virtual round of applause from everyone. And thanks to everyone for attending as well.
Thank you.
Thank you.
Thanks for having me.
Thank you. That was great.